In this video, we're going to see how knowledge of the properties of the basic trigonometric functions will enable us to produce models for some scientific phenomenon. Many scientific phenomena show features that repeat in a regular or near regular pattern, and we can describe such phenomenon as being oscillating phenomenon. Examples on this slide come from both medicine and astrophysics. Now in maths, we're familiar with the fact that if we're using radians for our angle measurement, then the sine and the cosine curves each repeat with period 2 pi. The amazing thing is that a large number of oscillating systems can be described using just sine and cosine functions. And in this video we're going to see that in a couple of relatively simple examples. But first of all, we've got to develop the major properties of the sine and the cosine graphs. If we've got the function y equals sine x, where x is in radians, then we know that the graph is an oscillation about y equals 0 of period 2 pi and of amplitude 1. And when x equals 0, the curve passes through the centre line of the oscillation and has positive gradient. Now what we want to do is we want to investigate a related graph. We want to investigate the graph of y equals p plus q times sine kx, where p and q are constants and k is a positive constant. And we want to work out what the significance of the constants p, q and k are. In the first place, we're going to keep k and q both fixed with the value of 1, and we're going to let p vary so we can discover the significance of p. And we're going to do that just using GeoGebra. So have a look at the little video that we've got here, and all that's changing is the value of p. And what you can see is that as p changes, so does the position of the middle of the oscillation. So we are able to conclude in this case that the graph of y equals p plus q sine kx is an oscillation about y equals p. Now let's see what the effect of changing k is. So this time we're going to keep p fixed at 1, we're going to keep q fixed at 1, and we're going to let k vary. We can see that the graph of 1 plus sine x has a period of 2 pi. And if we now turn the animation on, 1 plus sine 2x has period pi. The graph of y equals 1 plus sine 3x has period 2 pi divided by 3. The graph of 1 plus sine 4x has period pi divided by 2, or 2 pi divided by 4. And the graph of 1 plus sine 5x has 5 complete oscillations in 2 pi, so has period 2 pi divided by 5. So we can see that the graph of y equals p plus q sine kx has a period of 2 pi divided by k. So we now need to consider what the effect of changing the value of q is. So again, if we have a look at the video, we can see that changing the value of q is changing the amplitude. If q is a positive value, then the amplitude is q. If q is a negative value, then the magnitude is the modulus of q. So we are able to say that the graph of y equals p plus sine q sine kx has an amplitude of the modulus of q. And notice that when x equals 0, the curve passes through the centre line of the oscillation with positive gradient if q is positive, but with negative gradient if q is negative. Let's now have a think about the graph of y equals cos x. Well, we know that the graph of y equals cos x is an oscillation about y equals 0 with period 2 pi and amplitude 1, and when x equals 0, the curve has got a maximum point. Now we're going to consider the curve y equals p plus q cos kx, where p and q are constants and k is a positive constant. So again, we've got a video to look at. First of all, in the video, we're going to see the effect of changing the value of p. So as p changes, again, we can just see that the central position of the oscillation is changing. So we can see that y equals p gives us the middle position of the oscillation. If we now change k, then we can see that we're changing the period. And in each case, you'll be able to observe that the period is 2 pi divided by k. And if we change q, then we are changing the amplitude of the oscillation. If q is positive, q is giving us the amplitude, and if q is negative, then it's the modulus of q that gives us the amplitude. So we have then our properties of y equals p plus q cos x is an oscillation about y equals p, of period 2 pi divided by k, of amplitude the modulus of q, and when x equals 0, the curve has a maximum point if q is positive, but a minimum point if q is negative. So let's make use of these properties and try and do some predictions or produce some models for some graphs. So in the first example, we've got a 1 kilogram mass is suspended from a spring which is attached to a ceiling. The system is oscillating in such a way at time t seconds, the bottom of the mass is y meters below the ceiling. The diagram obtained from a motion sensor shows the relationship between y and t, and we want to get an equation, or a mathematical model if you like, relating y and t. Well, first thing is, when t equals 0, the curve is at its central position and has positive gradient. So that tells me that I have got a curve of the form y equals p plus q sine kt, with q being positive because we've got a positive gradient at t equals 0. The central position can be found by considering the extreme positions. The maximum value of y is 2, the minimum value of y is 0.8, so the mean position, or the centre of the oscillation, is going to be halfway between 2 and 0.8. In other words, it's going to be at 1.4. So that tells me that p must be 1.4. The amplitude of the motion is the modulus of q, and from the diagram we can see that the amplitude is 2, that's the maximum value, take away the mean value, which is 1.4, which gives me 0.6 as the amplitude. So we've got q must be positive 0.6. The period of the oscillation we can see is 2.5 seconds. The easiest way of seeing that is that you can see that we've got 2 complete oscillations in 5 seconds. So the period is 2.5 seconds. So we've got 2.5 is 2 pi divided by k. In other words, k must be 2 pi divided by 2.5, or if you like, 4 pi divided by 5. So we have the function describing the oscillation is y equals 1.4 plus 0.6 sine of 4 pi divided by 5 times by t. So we've got a mathematical model there to describe the motion of the mass. Here's a second example there. The diagram shows a relationship between the expected number of minutes of daylight in Cardiff, so that's t minutes, on a day which is little t days after the 21st of December 2020. So we're going to try and set up an equation linking little t and capital T, and then use that equation to predict how many days in 2021 does this model suggest we will have more than 14 hours of daylight. So if we look at the graph carefully at this case, we can see the graph is starting at its minimum value, which suggests that we have got a function of the form y equals p plus q cos kt, where q is a negative number. We can see that we have a oscillation that has a minimum value of 470 and a maximum value of 998, so the mean position is going to be the average of 470 and 998, which is 734. So that tells me that the value of p must be 734. The amplitude of the motion that we've got is the difference between 998 and 734, which is 264. Remember though that we've said that q must be negative, so the value of q that we've got is going to be minus 264. We know that the period of this oscillation is 365 days. So we've got the period is 365, it's the value of 2 pi over k. So that tells me that k must be 2 pi divided by 365, which is approximately 0.0172. So the model that we have got to describe the number of hours of daylight, the number of minutes of daylight that we're going to have is t equals 734 minus 264 cos of 0.0172 times by t. Now we can use this model to predict the number of days on which we're going to have more than 14 hours of daylight. So first of all, just remember that 14 hours of daylight means we're looking for the number of days in which we've got more than 840 minutes of daylight. So if I try and solve the equation, 840 equals 734 minus 264 cos of 0.0172t. Then we get minus 106 over 264 must equal the value of cos of 0.0172t. Doing an inverse cos then gives me 1.983, gives me a value of 0.0172t. So one value of t when we get 840 minutes of daylight is going to be when t is 115. So that's 115 days after the 21st of December 2020. There's also going to be another day slightly later on, and we can use the symmetry of the graph to find the other possible value of t. So you've got symmetry about t equals 182.5. So the other value is going to be 115 plus 2 lots of the difference between 182.5 and 115. And the other solution becomes 250. So that's telling me then that during the course of 2021, we're predicting 135 days a year with more of 14 hours of daylight. And our final example then, we're asked first of all to find an equation linking the variables y and x, whose graph is shown here. Well, that's quite nice and straightforward. Again, because we're starting with a minimum point, we know that we're going to have a graph of the form of y equals p plus q cos kx, with q being negative. The minimum value on the graph is y equals minus 5. The maximum value of the graph is y equals 37. So the mean position is going to be the average of minus 5 and 37, which is 16. So that tells me that p must be equal to 16. The amplitude of the motion, well, that's the difference between the maximum and the mean position. The maximum is 37. The mean position is 16. So the amplitude of the motion is 37 take away 16, which is 21. So the modulus of q is 21. So the value of q must be minus 21, because we've already said that q is negative in this case. The minimum points occur at x equals 0, and then the next one is at x equals 24. So the period of this oscillation is 24, which means we've got 24 equals 2 pi divided by k. In other words, we have got k is pi divided by 12. Equation linking the variables y and x is y equals 16 minus 21 times cos of pi over 12 times by x. Now, we have here a related graph which gives the temperature, theta degrees centigrade, in the desert, and how it varies with time, where t is measured in hours from midnight. So we can see that at midnight the temperature was 5 degrees C, and it went down to minus 5 degrees C at something like 4 o'clock in the morning, and then it got back up to a peak temperature of 37 at somewhere around about 16 hours into the day, at 1600 hours. Now the important thing to notice is that these two graphs are really very closely related. That if we take our original graph that we considered in part A and simply shift it by 4 units in the x direction, we will get the graph that we've got as our theta time graph. If we recall from our functions work that if we start off with a curve of y equals f of x and translate it by 4 naught, then we obtain the graph y equals f of x minus 4. Taking that in mind, we can see that our new graph is going to have the same equation as the previous graph, except y is replaced by theta, x is replaced by t, but it needs to be replaced by t minus 4 because of the translation effect. So the new graph has got equation theta equals 16 minus 21 cos of pi by 12 times by t minus 4, which can be rewritten as theta equals 16 minus 21 cos pi by 12 t minus pi by 3. So we've seen that using the trig functions we can get some useful mathematical models of naturally occurring phenomena.